Okay, well, as soon as we can get this PowerPoint up, we're going to be doing a video on Gibbs free energy and chemical equilibrium. Here we go. All right, my friends, without any explanation, you're going to see the following equation. This equation, excuse me, relates the change in the Gibbs free energy to the change in the Gibbs free energy under the standard state conditions. Remember, we defined the Gibbs free energy, the change in the Gibbs free energy, and the change in the Gibbs free energy under the standard state conditions in the previous video. Well, in this equation, the change in the Gibbs free energy is equal to the change in the Gibbs free energy under the standard state conditions plus R times T times the natural log of Q. R, as you can see, is the ideal gas law constant in the units of 8.314 joules per Kelvin mole, or the value of 8.314 joules per Kelvin mole. T is the temperature in Kelvin, and Q is known as the reaction quotient, which is something that you visited previously. This reaction quotient can be in concentration, but it can also be in pressure, or it can be in a combination of both. At equilibrium, we know that delta G is equal to 0. So if we replace delta G in the equation up above to 0, we also know that Q becomes equal to K when Q is equal to 0, because the two are the same, or excuse me, when delta G is equal to 0, Q and K become equal to each other because the two become one and the same. That's what I was trying to say. And so if we set delta G equal to 0 and replace Q with K, we get an equation that looks like this, that the delta G naught is equal to minus RT, the natural log of the value of K. And now you see we have a relationship between K and delta G under the standard state conditions. And of course, K informs us as to whether or not a reaction is favoring the forward reaction or the reverse reaction. And as we told you previously, delta G also tells us the same thing, or actually delta G naught. So here's a couple of charts. I never understood what they meant. You figure it out if you can. If you can't figure it out, ask Mr. Walsh. He knows everything. And I wouldn't worry about it if you can't figure it out. So as we said, K and delta G naught are basically telling us the same thing. We know when K is very, very large, much greater than 1, the natural log of K comes out to be positive, which causes our delta G naught to be negative. And the delta G naught being negative and our K being much, much greater than 1 is telling us that the forward reaction is favored over the reverse. When K is equal to 1, the natural log of K is equal to 0, and therefore the delta G under the standard state conditions is also equal to 0, which tell us that neither the products nor the reactants are favored one over the other. Oh, there goes the bell. And if it's a negative, if K is much, much less than 1, then our natural log of K is negative, which makes our delta G positive, and the reactants are favored over the products. That's the